In the video on the autoionization of water, we saw that you could have two neutral water molecules, but one of them could swipe a hydrogen ion from the other, and then you could be left with a hydronium ion, and the one that had the hydrogen ion swiped from it. Remember, a hydrogen ion is really just a proton. This one actually gains an electron. It gains an electron from that hydrogen. It takes all of the electrons from this covalent bond right over here, and it forms another lone pair, and it gets a negative charge, and that becomes a hydroxide ion. Or we could also describe that autoionization like this, that if I have one water molecule, well, the oxygen grabs both of the electrons from this lone pair, swipes hydrogen of the one electron it had, and all it's left with is its proton. So a hydrogen ion is oftentimes, it's really just talking about a proton, because the most common isotope of hydrogen only has a proton in its nucleus. It does not have a neutron. So you take away its electron, you just have that proton left. And the whole point of doing this to show, well, look, it's not going to be a typical thing. Most of the water molecules aren't going to be doing this, but this is going to happen if you have a large enough quantity of water molecules. And we've even seen to what degree that happens, how typical that is by looking at the concentration. If we looked at the concentration, so if we're talking about pure water, we've seen that the concentration, and we could think about it in two ways. If we think about this top way of expressing the autoionization, we could say the concentration of hydronium ions, or if we think about this one over here, we could think about the concentration of hydrogen ions. And the reason why these two things are equivalent is because these hydrogen ions are really just going to associate themselves with a water molecule and become hydronium. But in pure water at 25 degrees Celsius, we've seen that these are going to be approximately the concentration, whether you think of it as hydronium concentration or hydrogen ion concentration, it's going to be approximately 1 times 10 to the negative 7 molar. And what does that mean? Well, molar, this is just the units for molarity. That's the same thing as 1 times 10 to the negative 7 moles per liter. And if you have trouble remembering what moles are, first of all, I encourage you to watch that video on Khan Academy on moles, but you just have to remind ourselves it's a quantity. Just as a dozen means 12 of something, a mole of something means 6.022 times, and roughly 6.022 times 10 to the 23rd of that thing. So it's just a very, very, very large quantity. So that's the concentration, you could say the hydrogen ion concentration in pure water at 25 degrees Celsius. But we can ask ourselves that same question for other types of solutions. For example, orange juice. So let's just say right over here. So in orange juice, the hydrogen ion concentration, and once again, I could also say this is a hydronium concentration. Depending on your glass of orange juice, it wouldn't be atypical to find a glass that has a hydrogen ion concentration of, say, 1 times 10 to the negative 3.5 molar. So once again, this is actually a lot more than this here. Actually, let me make it a round number. You actually might be able to find something at 1 times 10 to the negative 4 molar. I looked it up on the internet. There's actually a range, kind of in the mid 3s to low 4s of hydrogen ion concentrations for orange juice. And so you could find something like this, and as you can tell, and it's good to always just think about the numbers, this is actually a much higher concentration than this over here. The exponent over here is less negative, so this is a higher concentration. And we could look at something that has a lower concentration, say something like bleach. I actually looked up, so bleach, I'll write that right over here. I actually looked it up on the Clorox website. The Clorox bleach, they say that their hydrogen ion concentration is approximately, so their hydrogen ion concentration is approximately equal to 1 times 10 to the negative 12. 1 times 10 to the negative 12 molar. So this is a much lower concentration than you would have in just water right over here, in pure water at 25 degrees Celsius. So this is a much lower concentration. This exponent over here is more negative. This is a lower concentration. Well, this is all well and good, but it can get a little bulky talking about concentrations in terms of, the scientific notation, something times something to the negative whatever molar. And so to help simplify that, people have invented the idea of a pH. A pH, and let me introduce it in a color that I have not used yet before. P, and you use lowercase p, uppercase h. And I've looked into where this notation comes from. The H, most people agree, is referring to the hydrogen in some way, but the P, some people think it's referring to potential. Some people just think it's a random letter that was it's just one of these historical artifacts. But this is defined as the negative log of, and we could say negative log, if we don't write a base, you assume it's base 10, but the negative log of the hydrogen ion concentration, or it's equivalently the negative log, because the hydrogen ions are really hydronium ions, H3O. It's really the same thing as this as well. So given this definition of pH, let's calculate the pHs for pure water at 25 degrees Celsius, or the pH of this glass of orange juice, or the pH of this bleach. Well, the pH of this pure water is going to be the pH. Let me do it so the pH here, so I'll have some space right over here. It's going to be the negative log, and I'll write the base 10 there just because that's assumed, of its hydrogen ion concentration, which is 1 times 10 to the negative 7 molar. And we want molarity right over here. You want molarity right over here. Well, 1 times 10 to the negative 7 is the same thing as 10 to the negative 7. And if you look at just the part with the logarithm before we think about the negative, this is just saying, to what power do we have to raise 10 to get 10 to the negative 7th power? Well, that's just going to be negative 7. And if what I just did is confusing, I encourage you to review logarithms on Khan Academy. So we're going to have the negative of negative 7, which is going to be equal to positive 7. So the pH of pure water at 25 degrees Celsius, and temperature would matter because it might affect autoionization, but the pH at 25 degrees Celsius is 7. What about this orange juice? Well, the pH over here is going to be the negative log of, instead of writing 1 times 10 to the negative 4, I can just write 10 to the negative 4. And of course, that's base 10. Well, what do I have to raise 10 to get 10 to the negative 4? We'll have to raise that to the negative 4 power. The negative of negative 4 is positive 4. By that same argument, or by that applying the same definition, the pH of this bleach is going to be equal to the negative log of 10 to the negative 12. I'm just ignoring this 1 times right over here. I could write 1 times 10 to the negative 12, but that's not going to change its value. And that, of course, is going to be equal to the negative of negative 12, which is positive 12. And so it might be fun to plot all of these. So let me do that. So let me plot these pHs. So let me draw a line right over here. And let's say that this is 0, 1, 2, 3, 4. Actually, I'm not going to be able to get all the way to 12, so I have to make that my scale a little bit smaller. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And I could keep going over here. So let me write this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So these are our pHs over here. I could plot them. That water at 25 degrees Celsius is going to be right over here. And that is my water. And that's sometimes referred to as a neutral pH. If I look at that orange juice with a pH of 4, that orange juice is going to be right over here. And I've seen ranges for orange juices actually more in this range right over here. So depending on your glass or whether it's gone bad or not. So that's going to be orange juice, could be found in that range. So I'll write orange juice. And then this bleach. And it depends on the concentration and all of that. But this bleach in particular is right over here. This bleach is right over here. And I can plot other things. If your stomach, the juices in your stomach are highly, well, I'll talk about the acidic a little bit more, but your stomach juices are going to be in, let me just hit a new color, are going to be in this range, right over here. So stomach, and often we're called, instead of stomach juices, stomach acid. And if you had something like seawater, it's going to be in this range right over here, seawater. Now let's think about what this is telling us. And remember, this is a logarithmic scale. As we go to the right, as we go to the right, our concentration is going down. It's important to recognize, and that's all because of this negative right over here in our definition. But we saw that bleach has a much lower concentration than the water has. So this is lower hydrogen ion concentration. And as we go to the left, we have a higher hydrogen ion concentration. Higher hydrogen ion concentration. And in general, if something has a pH below 7, we tend to refer to it as acidic. We say it is acidic. So typically when you add acids to neutral water, your pH is going to go down. It's going to get more and more acidic. And as you go to the right, if you have a pH above 7, sometimes you'll hear people say basic, and sometimes you also might hear people say alkaline. Alkaline. It is becoming more alkaline. Its hydrogen concentration is getting lower and lower and lower as we move to the right. And I really want you to appreciate the logarithmic nature of it, because if I handed you some seawater with a pH of 8, you might say, okay, no big deal, pH of 8 relative to a pH of 7. But this is a logarithmic scale. If we're moving to the right, we have a 10 times lower concentration of hydrogen ions. If we were to move 3 spaces to the right on this, where it's 1/10, 1/10, 1/10, we have 1,000th the concentration of hydrogen ions. So it's pretty interesting to think about how much lower the hydrogen concentration is in, say, bleach than in water, and how much lower that is than, say, stomach acid or orange juice.